Oops. Okay, good afternoon. How's everybody?
Good afternoon.
Yeah, hi. How are you, DeAndre? All right. So I see like 8 people here. um, oh, 7. What happened? Oh, okay. Isara is just joining. So 8 people, and there were like 9 people in the discussion board. Let me just. It's not a forum. Okay, I see. Yeah, 9 in the discussion, 9 in the forum. So, I guess still, I guess we still need one more person to join our collaborating session, but that's fine. We're gonna get started. So, we're since last, I guess yesterday, right? We've since yesterday we've been talking about the time value of money, but the time value of money. Literally, that means there's the value that is derived from time. I mean, of course, uh, today's $1,000 is not the same thing as $1,000 one year later, because always today's $1,000 is worth more than uh, future $1,000, because future is uncertain. I mean, there's uncertainty that comes with the future. So we have to discount the future, right? Which is called, if you discount the future value, then it's called present value. But all that we were, doing yesterday is under the, I mean, under the umbrella of time value of money, there are two types of models: single cash flow model and multiple cash flow model. So uh, we will, in the single cash flow model, basically the base formula, right, base compounding formula can be tweaked for different other unknowns, right? Because future value equals principal plus 1 plus, principal times 1 plus r raised to n. Okay, looks like gamma. But then we have of the four possible unknowns, right? Of course, P can be the unknown, principal can be the unknown. And solving for this is called discounting. R can be the unknown. So uh, solving for this, yeah, we can use geometric average. And what about n is the unknown? This is what we need to talk about today. So if n is the unknown, then uh, uh, from the base formula, right? Now, we could solve this for r, which is inside the parenthesis with the padlock on it. We could remove the padlock and we could free this guy, free r from the cell. Uh, but this time, n is the unknown. In other words, the padlock is the unknown. So then, how do we solve for the padlock? In other words, um, but the first thing is always, trying to simplify it as much as we can. And to simplify this formula, we'll have to divide both sides by p. Okay, so the left-hand side will become fv over p. The right-hand side will be 1 plus r raised to n. Okay, now it's back to this. So now it's fv over p 1 plus r raised to n. Now it's back to like z equals x raised to y. It's power function still. And again, at this time, this exponent is that's the unknown. That's what we need to find out. And how do we do that? So to do this, we will need to use log, right? To solve for. Why? Because log is, basically what log is basically expressing any, number, any large quantity by its own exponent, That's what basically the log is. Think about it. A simple example of log is 100 can be 100. We know it is. We all know it is 10 squared. Now, if we take the log of 100, right? If we take the log of 100 to base 10, okay? There are two ways to read it. You can read it as log of 100 to base 10, or base 10 log of 100, right? But either way, basically, you are doing this thing, right? 10 squared, log of, 10 squared, base to base 10. So in other words, what are we doing here? Using 10 as the base, right? We want to express 100 by its exponent. So if we then, basically log of 10 to base 10 is just 1. It's itself, right? What this means is, 10 to itself, 10 to 1, right? So that means log of 10 squared to base 10, and when we know this is 1, right? This thing is 1, but if this thing is 1, the whole thing should be 2. In other words, this is basically a way of writing log. Log has such a property. For example, if log of some number to the x power of x to base a, we can write it as x times log of a to base a. And if log of, so in other words, when we write something, when you express any number in log, this exponent can come down just like it can come down just like a coefficient, right? So in other words, think about it. This thing will be 1 anyway, right? This thing is 1, so it will just become x. So in other words, you're expressing this number by its exponent. So let's do a little more, just a few more examples. Base 10 log, base 10 log, right? Let's do a little more. So 1,000. If we take the log of 1,000, right? If we take 10,000, right? Why is it acting up? Okay, not equal, but not equal. If we take 10 to the third power, log of 10 to the third power to base 10. And then this turns into 3 times, right? Log of 10 to base 10, which is 1, right? So it's going to be 3. This is, we know it's going to be log of 10 to the fourth power to base 10. It becomes 4, and so on. Now, the example so far, was powers of 10. In other words, 10 squared, 10 third, 10 to the third, 10 to the fourth power, and so on, 10 to the sixth power, and so on. If we go on like this, all this, like million, billion, they can all be simply, think about it. 100 is 2, right? 1,000 is 3. 10,000 is 4, right? 1 million is 6. In other words, the exponents represent the number. And when we use the number, when you take the log of the numbers that are powers of 10, that's called common log. Right? So common log, it's easy to understand and easy to visualize what it is, because think about it. It's not easy to take the log of, common log of some numbers like 17.135. I mean, can you take common log of numbers like 17.135? Yes, you can. I mean, I wouldn't say you can, but the computers can. Human beings, to human brain, this is such a this is such a hassle for human brain to process, right? This is not, but it's not impossible. The computers can do that. But for human brains, common logs of the powers of 10 are easy to visualize. So what do we use the log for? So for example, suppose we want to show the distance between the Earth and our nearest galaxy, nearest solar system, or Alpha Centauri, right? Alpha Centauri is the nearest galaxy or nearest solar system, and I heard it is like 4 light years, 4 trillion light years. I don't think it is 4 trillion light years, but something like 4 light years. And 1 light years is like 800 billion miles or 8 trillion miles. I don't know. But think about it. If the distance between Earth and Alpha Centauri is that just like, let's just, simplify it. Let's say the distance is, like 10 to the 20th. Oh, I don't know how to. 10, 10 to the 9th is billion, right? 10 to the 12th is trillion. And 10 to the 15th is quadrillion, right? Well, how would you express such a distance, so 10 to the 16th would be, I don't know the name, quadrillion, so quintillion maybe, quintillion. But think about it. If we express even, let's say, then this is between Earth and, let's say, Sun. Between the Earth and Sun, the distance is, let's say, 10. Of course, it's not 10 miles, but let's say it is 10 to 1, right? But then 10 to the 10 squared is, actually 10 times this. Isn't it right? 10 squared will be 10 times this. But if we do it like that, 10 to the, even 10 to the 9th, there's no way you can put it on a limited space, right? If I have infinitely stretchable whiteboard, maybe on an infinitely stretchable whiteboard, if I stretch it, and if I put the distance between Sun and the Earth like this, and let's say that is 10 miles, it's not, but how far do I need to stretch to get to Alpha Centauri? Even if I stretch it all the way to West Coast, Los Angeles, maybe I won't be able to do that. So then, what's an effective way, or efficient way, or efficacious way, right, to express that distance, such a huge distance? Well, think about it. If we use logs, right? If we use logs, it's not a difficult thing, because on a log scale, this point will be 1, this point will be 2, 3, 4, 5, 6, and all the way to 20. Now then, what does this mean? Actually, 2 doesn't mean twice. It means 100 times, right? 3 doesn't mean 3 times. It's 1,000 times. 6 doesn't mean 6 times. This means million times. This means 10 to the, right? So, but this way, we can, if we use logarithmic scale, we can condense, we can condense huge quantity into more manageable, on a manageable scale, right? On a like manageable units, or what should I say? So that's the benefit of using log, okay? And as I said, the first benefit is the fact that we can right? The first benefit is that we can turn this into a multiplicative function, right? What used to be a power function, you can turn it into a multiplicative function. That's the first thing. Second, you can condense, or you can not truncate, but I think condense is a better way of saying. You can condense a huge quantity into more manageable uh, size, right? Uh, and then, so is common log is the only log? No, we can use any number as the base of the log, but what is commonly used is 10. 10 is the base, and then commonly used base. Also, there is a binary log, which uses 2 as the base. So that means log of 4 to base 2, that's 2, right? Log of log of 2, I'm sorry. Log of 8 to base 2 will be 3, and so on. That's binary log. And then there is there is natural log. And what is a natural log?
Is it the ln?
Yeah, that is, yes, natural log is expressed as ln, but it's just it's just how it is expressed surface. But question is, what is natural log? It's not a question that can be answered like that. ln is only the ln is only the outward look, right? Uh, it's like if you ask what is a university, oh, and it's like you're pointing to a building. Oh, that's the university. No, what is a university? Then we have more a profound concept behind it, right? So, what is natural log? Natural log is the log using e as the base. And what is this e? So natural log of x. E is it's called Euler's number. It's Euler's number. It's called Euler's number. Also called exponential function. Exponential. So what is e? Um, E is just like pi. It's an irrational number, meaning it's actually 2.71818, and it keeps on going, just like pi. But how did it come to have this name? How did such a number come to have that name? Because of the German mathematician named Euler. Because he discovered, or rather, he defined this number. Discovered or defined. It's not Euler, right? Because you don't, some people anglicize everything, but Euler's impact, his contribution to modern mathematics is so profound and so great, and obviously because he was like a Swiss German mathematician. So in honor of his heritage, right? It's very common to pronounce it in German, like exactly Euler. And actually, there are two very important German mathematicians that contributed so much to the modern mathematics. The other one is Gauss. Okay, so you might think all great mathematicians are German. No, in ancient world, great mathematicians were all Greek or Egyptian. And then in the Middle Ages, a lot of them were before Renaissance. A lot of them were Arabs, Arabic mathematicians. And then since after Renaissance, it's like French French mathematicians, Bachelier and who else? And then around like 16th, 17th century, 18th century, then Euler and Gauss, Swiss German. But what basically what is Euler's number then? How did it come to be this? How did it come to be this? So it's something like this. We all know M plays a very important role in compounding, right? And M can be, I told you, M can be 1 or 2 or 4, 12, 52, 365, etc., etc. Now, I've been telling you, 1 and 2 and 4 are quite common, right? 12, 365 also used, but when the banks are lenders, when the banking industry is the lenders. 52, not very often used, 52. But then, what is the, how far can you take it? How far? I mean, 365 is daily compounding. So then compounding, hourly compounding by the hour, is it? Yeah, of course. And 365 times 24, right? And then by the minute, you can do that. 365 times 24 times 60. By the second, you can do that. But then how far can you take it? I mean, if the compounding can be done by second, but then can it be done by 1/10 of a second, 1/10 of a second, 1/100th of a second, or nanosecond? In other words, 10 to negative 1, 1/10 of a second. That's 1/100th of a second, right? 10 to negative 2. 10 to negative 9, that's called nanosecond, right? 1/1000th of a second. It can be anything. But then what is the limit of all? I mean, can you, because the numbers are infinite, endless. I mean, there is billion, there is trillion, there is quadrillion, there is quintillion. I mean, there will be no end to it. However, so what is the ultimate limit that this M can go to? Of course, infinity, right? Think about it. Infinity is a number that is undefined because it is so huge, right? Nothing can be greater than infinity, right? And of course, what is this? Negative infinity? It's not negative infinity. It's still positive. It's just 1 over infinity. 1 over infinity. Isn't that right? That's 1 over infinity. So then this number will be infinitesimal number. Infinitesimal means infinitely small. Infinitely small. You divide 1 by infinity, will become an infinitely small number. Right? You might think, oh, isn't it 0 then? No, it's not 0. it will be close to 0, because think about it, you divide any number by infinity, it will have to be close to 0, but not quite 0, right? Not exactly 0, but something. Uh, and that causes, that poses an interesting question. That poses an interesting question, such as, so we know what. Right? And then this is how we adjust the APR and time for M, right? But suppose APR is 100% and time is 1, okay? 100% means, your money doubles every year, right? Because 100% return, right? But then, so if I rewrite this with 1 is 100%, right? Raised to 1. And suppose M goes to where M goes to infinity. And what does this thing become? It will become 1 plus 1 over infinity raised to infinity. And what's this number going to be? What is this number going to be? Now, as I said before, if this number will be a very small number, right? It's not going to be 0, but it will be something close to 0, something close to 0. Like 0.0000000000000000000, infinitely 0, infinitely 0, infinitely 0, infinitely 0, and finally 1 at the end. So that will be a problem. I mean, if this is exactly 0, right? If this is exactly 0, problem solved. Isn't it right? If this is exactly 0, the whole thing in the parenthesis becomes what? If this thing is 0, the parenthesis becomes what? Anyone?
1.
1, yes, of course. And who said that?
DeAndre.
DeAndre. Okay, so it's just a logical question, and only DeAndre can answer that. I mean, what about the other people? The other people are just, catatonic, like, brain, brain dead. Like you get catatonic. Let's say, you got electrocuted, and for a while, you will be obviously catatonic. Just, no, no, no brain function, but logically, we can all tell if this thing is 0, completely 0, then the value in the parenthesis is just 1. And if that is the case, the whole 1 raised to infinity, what's it gonna be? 1 raised to infinity.
To the
1
1.
raised to infinity. Yeah. It will just be 1. Who said that?
Mei Chen.
Okay, Mei Chen. Okay, DeAndre, you got 0.5, and Mei Chen. I don't know. To me, it's always. I have to put Q there, and phonetically, to me, it's Macon. Macon. So yeah, no matter what, you raise 1 to anything, it's still 1. 1 times 1 times 1 times 1 times 1 times infinitely times 1, still 1. So problem is easily solved if that's the case. Problem's easily solved. But then our problem is that uh, this is not quite 0. This thing is not quite 0, right? It's just slightly greater than 0. It's like the whole thing here in the parenthesis will be like 1.00000000000, infinitely 0 raised to, and then you raise that to infinity. It's something that's, so think about it, it's something that's slightly greater than 1, right? 1.0000000, infinitely 0 and 1, and you raise it to infinity. And what's it gonna be? And that answer was, it was answered by Euler. That's why it's called Euler's number. So this result is called Euler's number, and that's actually a number is like 2.71818, and so on and on and on. It goes on forever. But we don't really care, what we don't really use that. We just use this, right? We don't actually, because how can you we cannot, we just round off, pi at the second decimal place, 3.14. But pi goes on forever. Just like that, Euler's number E goes on forever, right? So we don't actually quote that number. Now the interesting, then the thing is, think about it. When m goes to infinity, what does that mean? That means continuous time, right? Why? Think about it. We think of time as discrete units because we treat it, time is broken down into years, and then it's broken down further into months, and then further into weeks, further into days, further into hours and minutes and seconds. So all those are discrete units. I mean, on a clock, in the old days, the clock, when you look at the second hand moved, in a discrete motion. The second hand is, let's say, this is the clock, and from 1 to 2, or the second hand was here, and 1 second later it clicks, it ticks, right? It doesn't move smoothly and continuously, but it moves discretely. It ticks, right? 1 second to the next, it ticks, tick, 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 tick. That is a discrete motion. It's a discrete move. It's not smooth. Well, these days, with the with the electronics and everything, the second hand is not ticking. It moves very smoothly, right? And if you think about it, time is a continuum. It's a smooth, in other words, time is not discrete thing. Time moves, continuously and seamlessly. That's what the time is, right? Time never declared itself. I mean, it's the human, it's the only human, contraption, right? It's a human contraption to divide time into months, days, weeks, years, hours and minutes and seconds. But time never declared itself in those discrete units. Time just flows seamlessly. So think about it. If we collect data, let's say we collect stock market, data, right? The stock price, of course, then um, so so we've collected stock price data. So this is time, and from the day one we collected data. And if we collected annual data, it will look, at time zero was like that. 1, 2. If this is annual data, you will see a lot of, you will see a lot of kinks. In other words, you connect them, it will look like this, right? So it's not smooth. And if we collected, like quarterly data, it will be smoother than this, because between this point and this point, at least there are 2 more data points. Okay, for quarterly, let's use. If we used quarterly, right? It will look smoother, right? It will at least look smoother. Connect those, it will look smoother. And if we used, so you know what I'm talking about. If we used, monthly data, it would look much smoother, right? If we used, daily data, it may be noisy. It may look more noisy, but it will be smoother. I mean, it may look more like this, noisier. Right? So what does that mean? If we use continuous time, and so can we have continuous data? Of course, there's no way to observe data in continuous time. But anyway, the idea of Euler's number, right? If we use Euler's number, because it is based on the continuous time, it can be the basis of like basis of log for real numbers. Real number means what? Real numbers are, real versus imaginary numbers. Imaginary numbers are something, when squared, it's a negative. Nothing can be negative when squared, right? But it's imaginary. On the real number, then there is integer and natural numbers. Think about it. Numbers are not only 1, 2, 3, 4, 5. There are like continuum, right? From 0.1, 0.2, 0.4, 0.3, but there's 0.01, right? 0.02. There is 0.001, 0.0002. Look, it's an infinite continuum, even between the integers of 1, 2, 3, 4. So those are called real numbers, right? So think about it. Because Euler's number is based on that continuous time. It can be the basis of log for any real number, right? If you use log as Euler's number as the base, this x can be any number, like It could be 0.0001756. Any real number can be, right? For that matter, I said, also, you can still, common law can do the job, but still, it's hard for human brain to process that, right? But anyway, it will be the computer that will process that. So knowing that, then we can take log of any number. Now we can come back to our problem. Our problem was what? Remember, we had all the way here, huh? PV over FE over PV is 1 plus R raised to n, and our unknown is this. But we know how to do this because now it is like z equals x raised to y, and I know if I take the log, I'll do it. If I take the log, then I can bring this down. And then it turns into a multiplicative function. And of course, when you take the log on one side, in the right-hand side, you have to do the same thing to the left-hand side, right? Because I've been telling you, it's an equation, meaning that equal sign must hold. And to do that, so now think about it. This is our unknown, right? And then we have log z to the left-hand side and log of x to the right-hand side. And then solving for y is easy. All you need to do is divide log z by log of x. Okay? Then we can solve for n, right? You can solve for. But then, our question is, what log to base what? Now we can use, we can take natural log because we don't know what this number is like, right? It may or may not be powers of 10, most likely not. And 1 plus r is certainly not powers of 10, so taking, common log is not the best choice. I mean, you can still do that, computers can still calculate that, but, considering that this is just any real number, right? Real number, which can be anything. I mean, 1.000 something, 1.00000 infinitely zero something. It can be something like that. And then how do we handle? I mean, that's why we have natural log. So we take the natural log on both sides then. So I'll call this natural log of a thing in the bracket. Just later we'll switch it. For now, I want to write FV over PV every time. And then this becomes n times, let me do it properly. The natural log of 1 plus r raised to n. And then the property of, this useful property, the n can be brought down like a coefficient. And natural log of 1 plus r. Voila! Now we can solve for n. So then n is what? The next page then. So then n will be natural log of f. Why is it doing this? natural log of fb over p over natural log of 1 plus r. And voila, that's the formula for n. Of course, you can just memorize this, but what's the point? I mean, you don't understand what natural log is and how natural log came, why it came about, how it came about, where did it come from, and all that thing, all those things. It's a long story. It cannot be just, right? It's like, what's a university? And, you can point to a building. Oh, that's the university. That's Vanderbilt University. That's Fordham University. That's, Columbia University. Yeah. But, the question is deeper, more profound. So, how did it come? Where did it come from? How did it, right? How did it come about? And to answer that question, you have to go through. Oh, yeah, this guy, who made a huge fortune, thought always he always thought he had to uh, contribute to the society and blah blah. Based on that idea, he founded this, university in 18 something. And at first, it was just on a land of, it was just two buildings on, 30 acres of land, only two buildings. Now it's 300 acres, whole campus is 3,000 acres, and there are 10 dozen buildings, and housing, and these buildings house, each, college, uh, school of medicine, and law school, and blah, blah. I mean, and so here we are now. Here we are. Why we are here, and this is why you are wearing this uniform, and why you are, taking this course. I mean, to explain all that, right? Uh, Not just pointing to the building and saying, "Oh, that's the university," but to explain, the whole story behind it, or the logic behind it. I mean, this is all about logic, right? In my class, I never just throw the formula at you and use this. No, you can't do that, because how would you memorize all those formulas? I mean, even if you are, even if you can memorize now, af- after the semester is over, probably in a matter of like weeks, you will forget everything. But if you understand the reasoning behind it, if you understand the logic behind it, you can always recover. I mean, you may have forgotten, but you can recover. You can trace it back, and you can recover, easily recover. But the rote memory will, and that's another thing. I showed you yesterday. You can use Excel's built-in function, but if you don't understand what is periodic rate, what is, n, you cannot use Excel's built-in function correctly, because you cannot make adjustment to the those variables, right? So that's the difference between the analyst and data puncher. Data puncher is what? Data puncher is a uh, uh, low-level job. Nothing but, anybody can punch in the data. You see the data, you punch it. But the data entry personnel, the data puncher, you can just input the data. Doesn't require a lot of, brain power, a lot of, analytical abilities, right? Just to input the data, uh, you can just hire someone who doesn't even have high school, diploma. They can just, input the data just mechanically, like a robot. But then, the analyst will not just enter the data, will not just input the data manually. They will think, oh, is this the right data to go in there? That's the difference. The ability to reason, the ability to reason logically, right? is this the right data to go in there? And that's the difference between a mere data entry personnel, data puncher, and an analyst. Of course, an analyst should at least have at least have at least a bachelor's degree, uh, a type of education like this, education focused on thinking, reasoning, logical reasoning, and analytical reasoning, and critical thinking, right? But just data entry doesn't require that kind of train. Even without high school diploma, you can do because you are just you're inputting the data mindlessly, right? And that's why I'm forbidding the use of Excel's built-in function because it just turns you into that data entry, data puncher, right? You understand? It's all about thinking. It's all about analytical reasoning and logical reasoning. Okay, so with that in mind, I think we can now start on the example, doing the example. But time is 7:01. I think it is the right time to take a break here. So let's take a 10-minute break. Let's take a 10-minute break and reconvene. Alrighty, we're back. We're back now. So let's go straight to the example. So everyone is looking at this. We stopped here yesterday, right? Everyone is on the same page.
Yeah, we stopped there.
Okay, good. So we're gonna excuse me. We're gonna start with row 23, right? What is going on? So we already know the answer. It will have to be 5, but let's see if it's going to be 5 when we do it by formula, right? So the principal is 10K, target future value 30K, and the going market rate is like 24.57. So let's take so natural log of future value divided by the present value, okay, divided by over natural log of 1 plus r. And in this case, that r is, it's just annual because m is 1, annual rate. So if you do that, it should give us exactly 5 years. Okay? Hit enter. There you go. You got 5, right? You got 5. Now, this time, let's try quarterly example. Quarterly, right? Quarterly compounding. So in this example, we do, natural log of FV over P, okay, divided by natural log of 1 plus, again, this is annual rate, so we have to divide it by M, right, which is in D25. So we enter it like that, but it's not going to give us 5 because if you do it, this is quarterly, right? So it will give us the time in quarters, not in years. So hit enter. It's 20 quarters, which is 5 years. So to answer it in years, we only need to what? Divide this, the whole root. We'll need to divide the whole result, entire thing, by, then again, D25. Okay, there you go. And then it gives us 5. Okay? Everyone is fine with that? Everyone is okay with that now? Everyone understands?
Yeah.
Okay, good. The adjustment that needs to be made, right? Now, so if you don't want all that, if you don't want all that, complication, we can go. We can, just add 2 more columns. The periodic rate at n, and then, okay, we'll just do, log of. Oh no, that's r. So r should be. We know what r is. It's APR divided by m. There you go. And we're gonna get 20 there. That's natural log of is 30K over 10K, and then divided by natural log of 1 plus r. Okay, 20. And if the problem was asking for time in years, then you just, you oblige. Whoever is asking the question, you oblige, by answering it in years. So then, simply then divide this by 4, and voila. Okay. Now, again, I don't want you to use Excel's built-in function. I mean, if you have to use it, you have to use it. But if possible, use the formula and try to minimize using or try to minimize or try to avoid dependence on because that's very dangerous. The dependence is very dangerous. So here, let's use Excel's built-in function. So what you're looking for is n. Okay, so you go to financial and n here, n periods, right? That's n periods, literally. Hit OK, and it's asking for first rate, right? And then again, if you click it in like that, no, you're wrong. You have to make that adjustment because it's quarterly. Okay, after rate, then there's no payment. There's no payment because this is a single cash flow. So we skip it, but you got to give it one comma so that that placeholder is a placeholder. It can be that placeholder can be respected, and then present value. Yes, this is the present value, and then comma, and then future value. Now, one thing here, one of them must be a cash outflow. One of them must be cash inflow, and one of them must be cash outflow. So then, which one? It doesn't matter. You can put present value as the or future value as. I mean, if the present value is the cash outflow, then you're making a deposit, right? And then the future value will be the cash inflow. And if the future value is the cash outflow, you are receiving the deposit. You're like you're the bank or the borrower. For the borrower, at time 0, there is cash inflow, but at maturity, there will be cash outflow. Either way, it doesn't matter. I'll make future value negative this time. Still, yeah. 20 quarters, right? It gave us 20 quarters, but if you want to turn it into years, then of course, then you'll have to. It gave us 20 quarters, so you divide it by m. Then that will give us 5 years, right? It will give us 5 years. So we can use Excel's built-in function, but you have to be careful when you use Excel's built-in function, right? It always eventually it falls upon you. It's your responsibility to make sure that it is doing the right thing. In this formula, if you didn't do this, then it's going to give you just 20. And unless you clearly state that it is 20 quarters, then a third party person can consider it as years, 20 years. So you have to make sure it is in the right form. Okay. And then, so that wraps up everything. That's everything about single cash flow model. Now, after single cash flow model, we are moving on to a multiple cash flow model. But multiple cash flow model, we'll have to. Okay, I'm gonna go back to this whiteboard. And I told you earlier that the, oops, it's stuck, it's frozen. Okay, now it's moving. Okay, single cash flow model is so cold. It's called a single cash flow model because there is only single cash outflow and single cash inflow, right? Think about it. If this is cash outflow or negative cash flow, that's cash outflow, this will be positive cash flow or cash inflow, right? You make a deposit, that's cash outflow. In the future, N years later, you'll have, right? But there's a single cash inflow, single cash flow. But it's not the only way because multiple cash flow. Now think about it. There are. It can be broken down into annuity and free form. Free form. That's my terminology. Free form, right? Annuities. This is more important. Annuity is what? What's annuity? So annuity is basically, annuity sounds like something annual, or it doesn't have to be annual. It can be annual, it can be quarterly, it can be monthly, it can be, semi-annual, it can be anything, right? But the point is, annuity is a regular amount deposited or paid at regular interval. Okay, that's annuity. So regular deposit, regular amount paid or deposited at regular interval. Okay, so there's a regular. And if you think about it, a lot of when you borrow money, if you get a loan, right? If you get a loan, suppose you got a $1 million mortgage loan to buy a building, $1 million mortgage, and let's say this is a 30-year mortgage, 30 year. We all know nobody's naive enough to think that, oh, so what I pay back is this principal is 1 million, and if interest rate is 10%, 30 years, oh, so 30 years later I'm gonna pay back. No, nobody waits 30 years, right? When they lend money, the payment starts right the next month. The payment starts already, right? So as you are making, so for 30 years you are making monthly payments, which are 360 payments. So think about it. This is a regular payment at regular interval, right? Uh, so this is annuity, right? This is annuity. It's a multiple cash flow model because there was a single cash flow to you, cash inflow to you. You got $1 million. But then from then on, every month, at the end of every month, there will be payments, right? Multiple. There are 360 of them, so it's multiple. Okay. Uh, so let's take a look at the example of okay, so there is in annuities. So we'll take a look at the annuities first, and then of course there is future value of annuities and present value of annuities. Okay, future value of annuities first. Okay, let's take a look at the example. Okay, so one example is that the graduate school fund. Okay, so you're preparing for graduate school, and your timeline is 5 years. So in 5 years, you want to go to graduate school. So let's say uh, you want to go start take an MBA program, right? You want to get an MBA, so you want to. And it's going to take 2 years, 2-year program. Um, but you have to first graduate from college, and it's going to take 5 years for. I mean, if you work, uh, if you're a full-time student, generally it will take just 4 years. But let's say just to be on the safe side, 5 years. Well, then how would you? And how much is going to cost? How much is it going to cost? Uh, uh, the MBA program. How much is it? And CUNY, if you go to CUNY, because CUNY is the most affordable school. If you want to do MBA in like Ivy League schools, Columbia would cost you probably at least 50K to 60K a year. Even if it is a graduate, I mean, you all know Ivy League schools, cost about 60K a year, the undergrad. And most of the undergrad programs, cost a lot of money because a lot of that is not just tuition but room and boarding, right? If you go to Princeton or Yale, Harvard, MIT, you have to live in the dorm, right? And you have to eat there. You have to eat in the school cafeteria. So it's room and boarding, right? And meals. It takes a lot of, and then, so let's say about, half of it is tuition, half of it is, room and boarding. That's why it's so. But if you are a graduate student, you don't, there's no, dormitory is not mandatory. Dormitory is not mandatory. There's a rhyme there. In other words, room and boarding is not mandatory. You can, just from the apartment, you can live on your own, in an apartment or whatever, whatever cheapest, room and board. Uh, the meal, you can cook your own meal. But even then, it will still cost a lot of money, uh, just tuition alone. Uh, so obviously, then your choice will be CUNY school, right? Zicklin Business School. And I guess it would. I don't know. I don't know how much is, but because it should be a affordable school, so it will be about half the Ivy League schools, something like probably 30K a year. So for 2-year program, it would cost you 60K. So then next question is, how are you going to amass this 60K? How are you going to? uh, uh, put you through the graduate school. So your idea is okay. So I have 5 year timeline. So during this 5 years, I get a part-time job, and from my part-time job, at least I can save $800 every month. So I'm gonna deposit $800 every month with interest. I mean, $800 for 5 years alone is not gonna take you to 60K because 800 times 60 months, 5 years, 60 months, will only take you to 48K, 48K, right? So it's still lacking, 12K. But with interest, I mean that's just the principal alone. So with interest, you may be able to get there. I mean, if the interest rate is good. So we'll find out. We'll see. So to prepare for graduate school in 5 years. So you see, with APR, currently the market rate is 6%. So will you have saved enough to pay for your graduate education in 5 years? Let's find out. But then first, take a look at this concept. So the annuity is, this is the future value of annuity. This is a very simplified version because in this example, you're making a deposit, and deposit and payment are the same thing. They are. You might think, how can they be the same thing? But it's the same thing, only looking at it from a different uh, side of the table, right? If you're the lender, uh, if you're a borrower, uh, it's the payment. If you're the lender, uh, I mean, the payment is being deposited every month, so it's two sides of the same coin. Now, in this example, the timeline is 5 years. So this is very simplified example. And you make $1,000 deposit at the end of each year. And the interest rate is 20% a year. Interest rate is 20%, APR 20%. Then what are you going to have at the end of 5 years? So the idea is then, it will be the first deposit will earn interest compounded 4 times. First deposit will earn first deposit will earn interest 4 times compounded, right? Because it's going to be 1, 2, 3, 4. Second deposit compounded 3 times. Third deposit compounded 2 times. Fourth deposit just once. Last deposit doesn't earn any interest because technically it is called deposit, but think about it. The minute you put it in there, you take it out. The minute you put it in there, just take it out. It's just like there's a dipping sauce, and you want to dip the chip in it. At least you gotta dip it and keep it there for a couple of seconds to have the dip on it. And consider that dip the interest. But let's say in this case you just dip it and take it out right away. So the chip touches the dip, but it doesn't have. You take it out right away. So there's not enough time for the chip to gather uh, the dip around it, right? So it's just like so. Last one doesn't earn any interest, but at the end of year 5, this is how much you will have because that's the sum of the future value of everything, right? Now, in this case, in this example, the deposits were made at the end of every year, at the end of each year. But consider another case. Another case, this is the numbers are different, but basically 5 year timeline, and you're making the deposit at the beginning of each year. And if you are making deposit at the beginning of each year, think about it. First deposit will earn interest 5 times compounded, right? 1, 2, 3, 4, 5. Second deposit 4 times, right? So, and even the last deposit earns interest 1 time, right? because you're making that deposit at the beginning of the year. So then think about it. The only difference, the difference between the two is that every deposit earns interest one more time than this case. Now, the case above is called ordinary annuity. Ordinary. And ordinary means that it's the default. Ordinary means that it's the default, right? A second case is called annuity due, right? Annuity due, right? It's called annuity due because that means payment is due already to begin with. Okay, and so unless it is specifically mentioned or stated in the problem that it is annuity due, basically the default is always the ordinary. Okay, default. And also think about it. If you are getting a part-time job, you cannot make a deposit at the beginning. I mean, you start the job at time zero, you cannot make the deposit because you haven't got paid yet. You start the job, and at the end of the month you'll get paid. Then you can make a deposit, right? So it's like so ordinary is quite natural, ordinary annuity. And then if I put this idea on the graphically on that, where is that thing? Okay. The idea is like this. The first deposit, first of all, first deposit, deposit is called payment, right? We'll earn interest. This is, of course, monthly rate, n minus 1 time. Isn't that right? And in our example, our n is 60 months. But because I'm making a deposit at the end of the first month, from the end of the first month to the end of the 60th month, it's 59, right? Less n minus 1. And the second deposit will earn n minus 2, interest compounded n minus 2 times, plus, and it keeps on going like that. It keeps on going like that. And then the second from the last deposit, third from the last deposit, third from the last. In other words, 58th deposit will earn interest 2 times. Isn't that right? 58th deposit will earn interest 2 times. And the 59th deposit will earn interest just once. And finally, I should write it there. Finally, right? The last deposit, 60th deposit, earns nothing, right? So we can put it like this, or we can organize it more like this, starting from, because it's the smallest number is this, from the smallest to the biggest. Payment times payment times 1 plus r, right? Plus payment times 1 plus r squared plus that ellipsis plus payment 1 plus r n minus 2, and then plus payment 1 plus r raised to 1 minus 1, n minus 1, right? So Of course, this is, very tedious job. I mean, because you cannot write out 60 terms like this. Uh, so a better way of writing this is, you already know, the summation sign. Summation sign. You can write it like this, where t runs n. What do I where n runs from 0 to t minus 1, payment times 1 plus r raised to n. Okay, t, uppercase T is always the terminal time, or the maturity, terminal time. So now think about it. This captures everything, right? When n is 0, it's going to be just the payment, right? When n is 1, it's going to be payment times, 1 plus r. N is 2, payment times 1 plus r squared. And all the way to, if t is 60, right? If t is 60, it goes all the way to 59. But then our next question is, so, okay, this is a nice way of, expressing the whole idea compactly, or, concisely or compactly. But how does it help us to calculate it actually? Right? Isn't it right? This is a nice way of capturing the idea, a compact way, but it doesn't really help us calculate it. Because to calculate it anyway, you'll have to expand it like that. So we need a formula. Well, actually, the formula is, I can, the reduced form formula. I mean, we know the formula is, then the future value of annuity. Formula is payment times 1 plus r raised to n minus 1 over r. Okay. The question is, how did we arrive? How did you arrive? How do we arrive? How did you arrive at that? How did we arrive at that formula? I'll show you how we arrive at the formula, right? But for now, that suffices to know. For now, I'm gonna explain how. So let's find out. Let's find out. So here's our example. This is exactly our example, isn't it right? Because you make deposit of $800 every month. APR is 6%. The timeline is 5 years, right? M is 12 because it's monthly, right? So the first thing you need to do is, okay, what's the periodic rate? Of course, you divide 6 by 12. It's going to be 0.5%. Not 5%, but 0.5. Why? Of course. But also you can think, if APR is 6%, if APR is 12%, wouldn't monthly rate be just 1%? Yeah, of course, 12 do. So then, if it is APR is half of that, yeah, it will have to be half of 1%. Monthly rate will be. So, okay, get you. Now, we know it's going to be 60 total number of compounding, right? Actual number, because 5 years is 5 years, and times 12, right? Hit enter. Okay, and then using the formula, right, future value of annuity is payment times open parenthesis, okay, open another parenthesis because you have, there's an outer bracket and 1 plus r as outer bracket and inner bracket and raised to 60 minus 1, right? And then this whole thing needs to be divided by r, right? That whole numerator must be divided by r. And hit enter. Okay, there you go. We got something. Now, but it's too soon to celebrate yet, right? Because some people might say, oh, hooray, I got it. You got what? You got the future value of those, $800 annuities, but what situation are we in? Why did we do this? We did this because you have graduate school plan, right? Plan for graduate school, and you want to know you need $60,000 to, pay for the graduate school. That's why that's what started all of this. So our question is then, eventually, our question is, did we meet our goal? Did we meet our goal? Of course not. We haven't met our goal yet because our goal is 60K. We just got the future value of all those $800, but then it still falls about $4,000 short. Isn't that right? It still falls about $4,000 short from that, target future value, right? We have target future value and we are falling short of that. So then, what can we do? Well, we can explore alternative scenarios. What are the alternative scenarios? Well, we raise our monthly deposit to, let's say, $850. One possible alternative is one other option is raise our monthly deposit to $860. Okay. Another one is we find a bank that pays higher interest rate. But is it likely? I mean, can we find a bank with higher interest rate? Realistically, no. Why? Because I've been telling you, banking is a very competitive industry. From one bank to another, interest rate doesn't vary that much. I mean, you can find some bank that pays 6.5%, but that's already a big deal. It's not going to be easy to find not going to be easy to find a bank that pays like 2% higher than the average uh, rate, going rate. But let's say we found something like 8%. Another option is, okay, so you see what I'm doing here. Another option is find a bank that has, or extend your timeline. Extend your timeline. Another option is extending your timeline. Okay, so one option here is increasing the, right? Another option is this. Another option is this. Under those three different, no. Under those three different scenarios, right? Okay, stop. Under those three different scenarios, we can compare those. We can do sort of scenario analysis. We can compare those three different scenarios in a single shot. Why? Because you can. That's what the Excel is good for. highlight those 3 cells and just drag it down. Okay, and then what do you see? Oh, if we increase our monthly deposit by $50, then we are much closer. We're just about $700 short. Isn't that right? And then if we find a bank that pays higher interest rate, 8% interest rate, we are closer, but not than this one. We're still about, $1,200 short, right? And then this one, oh, if we extend it by 1 more year, we postpone it by 1 year, extend the timeline, and we will have more than enough money. Okay, well, I don't know. You may pick option 3, or I don't know, maybe option 4. This is option 1, option 2, option 3, 4. But then it is postponed by 1 year, right? So our question is then is there a way now? When we increased our monthly deposit by $50, we were like, this is the closest we could get, right? So then our question is, oh, what if we make it 860? Well, I change it to 860. Oh, then we hit our target. It would, but we overshot. We overshot our target by $2. That's almost as good as, but that's good. But you might wonder, what if we want to really hit 60K? And our question is there a way we can exactly nail this? Exactly nail the correct payment? Yes, there's a way we can do that. Before that, what I just did so far is called, trial and error method. Trial and error. What is a trial and error? Literally, we try out different possible numbers, and we experience errors, right? But through that, we will eventually narrow down. We will narrow down the possible range, and then zero in on the. But again, that's so much iterative process, isn't it right? It's so much iterative process. And there's no guarantee that you will get it right, within 10 trials. It could take, more trials than 10. So that's not a very efficient way, right? Trial and error method is not an efficient way. So, well, we can nail exactly. We can nail it exactly. In other words, how? Because we can solve this equation for payment. Then that's it, right? We can solve this equation for payment, and we can nail it. We can nail the exact. Another option is it's not option, but this is ordinary annuity. But let's suppose it's annuity due. If it is annuity due, how do we calculate it? How do we find annuity due? If you remember that you see, the only difference between ordinary annuity and annuity due, what is the difference between ordinary annuity and annuity due? Anyone? Anybody there? Hello? Anybody there?
Yeah.
Okay, Macon, hi, Zora. At least 2 people are there. 2 people are, watching and paying attention and breathing, and but the rest of the class, I don't know where they are. Huh? Leo Wen, are you there, Leo Wen? Leo Wen? I don't see any vital sign. Okay, Leo, you are there. Okay. Maximino Garcia, are you there, Maximino? No vital
I'm here.
sign.
Yeah, I'm here.
Oh, you okay? Good, you're there. Andreas Gori, are you there, Andreas? Andreas? Okay, no vital sign. Uh, Bria Benjamin, are you there? Bria Benjamin? Hmm? No sign. DeAndre, I'm sure you. DeAndre, are you
Yeah,
there?
I'm here.
Okay, you right. Uh, and then Elena Avestian. Elena, are you
Yes,
there, Elena?
I'm here.
Okay, so I have everyone. Uh, I have everyone. 10 people. How come nobody is responding? So okay, so back there. My question was, I was saying, yeah. What is the difference? What's the difference between the ordinary annuity and annuity due? Hmm? What's the difference between the ordinary and annuity due? I already said that. And so when I ask this question, some people will always say, in every class, right? When I ask this question, there is always someone who says, "Oh, ordinary annuity is, starting from the end of the first period. Each period, the payment or deposit is made at the end of the period. Uh, Annuity due is, making a payment or making a deposit at the beginning of each period." No, no, I'm not talking about that. Yeah, that's the definition of ordinary and annuity due, ordinary annuity and annuity due. But once again, that's like uh, to a question, what is a university? So let's say, who knows? This is a profound question. Uh, to that question, just pointing to a building, oh, that's the university. That's like, answering like that. Uh, to the question, what's the difference between ordinary annuity and annuity due? I already said that. One more compounding is the difference. One more compounding. Isn't it right? Structurally, there is one more compounding for annuity due. There is one more compounding. The first payment, first deposit, uh, in this example, only compounded 4 times, 5 times, 3 times, 4 times, 2 times, 3 times. So every deposit gets compounded one more time, right? Then mathematically, oh, no, 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 no. What did I do? I accidentally closed it, but okay, I guess I can. I'll open it here again. Okay. So how do we find the annuity due? It's one more compounding. So I can recycle this. All you need to do, recycle that, right? That result will get compounded one more time, right? That's the annuity due. Hit enter, and you drag it down. And voila, you have uh, annuity due. Again, uh, still this comes out as the best option for now, but uh, we overshot. But anyway, as I told you, we can solve this equation for payment, right? We can solve this equation for payment, and we can nail the exact payment, right? You'll be surprised that it's quite close to this number. We'll do it tomorrow because we're already, out of time. That's all the time we have for today. Okay, so if you have any questions, please email me. And as I said, I'm fully booked until Wednesday. The only so this week the only office hour opening is on Thursday. So whoever, it's first come first served. So whoever sends me email first will get that spot. Um, so okay, so that's it for today. Have a great night or evening or night, and we'll see you tomorrow. Okay. All righty. Take care, everyone.
All right, good night.
All right.
Okay.
Good night.
Pleasure. Good
All
night.
right. Take care. Take care. So I'll stop recording.